You know how sometimes it feels like unlocking really advanced AI demands? Well, basically a supercomputer.
Oh, absolutely. The cost, right?
Yeah, the sheer cost of running these massive language models, the memory they just gobble up, the energy they consume, the time it takes, it can feel totally out of reach for most of us.
That's a really crucial point. We've seen these incredible leaps in what AI can do, but yeah, it's often been tied to needing ever more powerful and, frankly, expensive hardware.
Definitely. It raises a real question about who actually gets to benefit from this tech.
Mm-hmm.
Okay, so let's unpack this, because today's deep dive is into some fascinating research that suggests maybe a completely different path.
Oh.
We're diving into the technical report on BitNet b1.58 2B4T. It's the first open source, what they call native 1-bit large language model. And it's got a pretty substantial, 2 billion parameters.
Right, I saw that. And that term 1-bit there is really key, isn't it?
It really is.
It hints at a fundamental shift in how these models represent and work with information.
Exactly. And for you, the listener, this is where it gets really interesting. Imagine getting a solid understanding of a potentially game-changing development in AI without getting totally lost in a sea of technical details.
Right.
We're here to extract the core insights, those aha moments, as we explore how this could maybe democratize access to powerful AI.
So our mission today is basically to clarify what makes this BitNet model unique, how it manages to achieve so much with what sounds like, well, so little computational muscle, and why the researchers think it's such a significant step forward.
At our main source, this technical report, it's just packed with information. It gives us a detailed look at how well BitNet performs across a whole range of tasks, understanding language, tackling complex reasoning.
Problems coding.
Exactly, even writing code and just having conversations. Plus, we get the inside scoop on its innovative design, how it was trained, and crucially, the efficiency it promises.
Okay, so let's start at the beginning. What exactly is a 1-bit large language model?
Right. Think of it like this. Typical AI models, they use lots of bits to store their knowledge, right? Imagine like a painter with this huge palette of colors offering incredibly fine distinctions.
High precision.
Yeah. Model quantization is kind of like simplifying that palette using fewer colors to represent a similar picture. Now, full precision models use that big detailed palette for every single piece of information.
And a 1-bit model takes this simplification, well, to an extreme. Instead of that full spectrum of colors, we're essentially talking about a switch. It's either on or off, positive or negative.
Pretty much.
Precisely. In a pure 1-bit model, the weights, which are, the core parameters holding the model's knowledge, they're limited to just 2 values, often -1 and +1.
Okay.
Some go a step further and use 3 values, -1, 0, and +1. And this just dramatically slashes the amount of memory needed.
Which is the big draw.
Absolutely. You could potentially go from needing gigabytes of storage down to just megabytes for a sort of similar level of understanding. And BitNet b1.58 2B4T uses this 3-value approach, employing what they call 1.58 bit weights, those -1, 0, and +1 values.
Right, that specific number.
Yeah, and that seemingly small fractional bit, the 0.58, it makes a surprisingly big difference in what the model can actually learn and represent effectively.
Now, the obvious question you might have is, okay, fine, you save memory, but doesn't squeezing the model down to just 1 or 1.58 bits completely wreck its performance?
Yeah, you'd think so, wouldn't you?
And that's where the word native in its name becomes really, really important for you to understand.
Exactly. There's a huge distinction here. You can take a fully trained, high-precision model and then try to compress it down to 1 bit afterwards. That's called post-training quantization, or PTQ.
Right.
But these PTQ methods, they often lead to a noticeable drop in how well the model performs. It's kind of like making a super detailed photograph and then just reducing it to only black and white.
Yeah.
You inevitably lose a lot of the original information.
Right. You lose all the subtle shades, the nuances. But a native 1-bit model, like this BitNet one, it's different. It's trained from the very beginning with these 1-bit constraints in mind. The researchers have designed the entire training process to work optimally with this, extremely limited precision.
So previous attempts at open source 1-bit LLMs have either been those post-training quantization efforts, which, as you said, often sacrificed performance, or they've been native models, but much smaller scale. We're talking maybe hundreds of millions of parameters, not billions.
Right, not this big.
Yeah. BitNet b1.58 2B4T is the first open source native 1-bit LLM to reach that significant 2 billion parameter scale.
Yeah.
That's actually a major step forward.
And the results they achieved are, well, genuinely eye-opening. This model was trained on an enormous amount of data. Get this 4 trillion token.
That's a lot of tech.
That's a T for trillion. To give you some context, that's like reading, I don't know, thousands upon thousands of books.
Well, that massive amount of training data is absolutely essential, right, for any large language model to develop a deep understanding of language and, the world.
True. But the really exciting finding, the core takeaway is this. Even with these ultra-low precision weights, BitNet b1.58 2B4T performs on par with leading open-weight, full-precision LLMs of a similar size.
Okay, hold on. On par.
On par. Think about that for a second. Comparable intelligence, basically, with just a fraction of the computational cost.
That efficiency is really clearly illustrated in their report, Figure 1. They call it the Pareto frontier of open-weight LLMs.
Right.
And it visually demonstrates that BitNet, well, it achieves a much better balance between performance and memory usage compared to models like, say, Llama 3.21b, that's 1 billion parameters, Gemma 3.1b, also 1 billion, and even the Quena 2.5 family up to the 3 billion parameter mark.
So it's punching above its weight memory-wise.
Exactly. It's using significantly less memory for the same level of ability, and in some cases, maybe even better ability. For you, the listener, this could translate directly to running quite sophisticated AI on much less powerful hardware.
And it's just some concrete numbers on that. Table 1 in the report gives us a detailed breakdown on specific benchmarks like complex reasoning measured by ARC challenge. BitNet scored 49.91.
Which is pretty good for that benchmark.
Yeah. To give you a sense of scale, it outperformed Llama 3.21b, which scored 37.80, and Gemma 3.1b at 38.40.
So a significant jump there.
Right. For you, this means a noticeable improvement in the model's capacity for complex thought compared to those specific models. For general knowledge, the MMLU benchmark, BitNet was at 53.10, which is, competitive with something like Qwen 2.5 1.5b at 60.25.
Still in the ballpark, yeah.
And when it comes to math, on GSM-8K, BitNet achieved 58.38, even surpassing Qwen 2.5 1.5b score of 56.79.
Okay, so it's holding its own, and even winning in some areas. But what's really striking is that while, maybe some full precision models might still outperform BitNet on very specific tasks,
sure,
its overall performance is remarkably strong, especially when you factor in that incredibly low non-embedding memory footprint, just 0.4 gigabytes.
0.4, that's tiny.
It's a tiny fraction of the memory those other models need. This dramatic reduction, well, it opens the door for running sophisticated AI on devices you might already own, right?
And it gets better. The estimated energy consumption during decoding, that's when the model is actually generating text, is also significantly lower. That's shown in the same Table 1.
Or power draw nice.
Plus, on standard CPUs, they measured a latency of just 29 milliseconds for BitNet to generate a response.
Wow, that's quick.
Which was faster than the listed times for those other comparable models in the table. So not only is it smaller, it's potentially faster and more energy efficient too.
So the crucial question for you listening is, how on earth does it manage this? What are the key architectural innovations? How does it perform so well with such incredibly low precision weights?
Yeah, what's the secret sauce? The report highlights a fundamental change in the model's design. They've replaced the standard full precision linear layers within the transformer architecture.
Those core building blocks of most LLMs.
Exactly. They swapped those out with their own custom designed bit linear layers. This seems to be the foundation of its efficiency.
Okay, bit linear layers. And within those, the weight quantization is where the real magic happens, presumably.
Seems like it. They use this specific technique called Ebsnine quantization to compress those weights down to those 3 possible values, America 1, 0, and +1.
Ebsnine, right.
It's all about intelligently representing the essential information with this very limited palette, The researchers found that this specific method helps maintain training stability and, importantly, retain crucial knowledge despite the compression.
Okay, so that's the weights. What about the activations, the signals flowing between layers?
Good point. They also quantize those activations down to 8-bit integers. They use a different method here called ABSMAX, and it's applied per token. This further contributes to the model's overall efficiency.
So weights are 1.58-bit, activations are 8-bit. Got it.
And to make sure everything remains stable during the training process, especially with these low precisions, they've incorporated something called subline normalization.
Right. Stability is key when you're pushing these boundaries. Another interesting design choice mentioned is the activation function they use in the feed-forward network part of the transformer block.
Uh-huh.
Instead of the more common swidge LU, they've opted for squared ReLU, or ReLU squared.
Why that?
Well, the reasoning they give is that it might encourage more sparsity within the model, meaning more of those one-bit weights end up becoming 0.
Ah, okay.
And that sparsity can lead to better computational characteristics, especially when you're dealing with these ultra-low precision values. It potentially makes the math easier, faster.
Makes sense. They're also using rotary position embeddings, RoPE.
Yep, RoPE. That's pretty standard now in modern LLMs. It helps the model understand the order of words in a sentence, which is obviously critical.
And similar to the llama family of models, they've apparently removed all the bias terms from the linear and normalization layers.
Right, which also helps chip away at the total number of parameters the model needs to store and compute. Every little bit helps when you're aiming for this level of efficiency.
And just quickly, for processing the text itself.
They're using the same tokenizer as Llama 3. It's a byte-level byte-pair encoding, BPE, with a pretty large vocabulary of over 128,000 tokens.
Which is good for compatibility, right?
Yeah, exactly. It's beneficial for you because it ensures compatibility with many existing data sets and tools out there.
Now, okay, training a one-bit model from scratch must present some pretty unique challenges compared to training a standard full precision one.
Oh, absolutely. It's not just business as usual.
The report details a three-phase process they used.
That's right. They began with a large-scale pre-training phase. That's to give the model that broad foundational understanding of language and, how the world works.
Phase 1.
Then they moved on to supervised fine-tuning, SFT. That's where they teach it to follow instructions properly and engage in more natural, helpful conversations.
Right, making it useful.
And finally, they use direct preference optimization, DPO. This is to align the model's responses more closely with what humans actually prefer, what we find helpful and harmless. And crucially, DPO does this without needing to train a whole separate reward model, which simplifies things.
Okay, so pre-training first. In that phase, they used a rather clever two-stage learning rate strategy. They started with a relatively high learning rate that gradually decreased over time, like a cosine decay. But then about halfway through training, they sharply reduced it to a much lower rate for what they called a cool-down period.
Interesting. Why the two stages?
Well, the researchers apparently found that these one-bit models can actually handle more aggressive, higher initial learning rates than full precision ones. So they push it hard early on, then ease off.
And that cool down phase with the lower learning rate, that was crucial. It allowed the model to really fine-tune its understanding, particularly as they fed it a set of higher quality training data during that period.
Better data later on.
Yeah, this targeted approach helps solidify the knowledge gained during the initial, more aggressive phase.
They also implemented a two-stage weight decay strategy, to prevent the model from just memorizing the training data, overfitting.
Standard practice, but maybe adapted here.
Yeah, they applied it during the initial phase, but then essentially disabled it during the cool down. And the data itself for pre-training was a really diverse mix: web crawls, educational materials, and even specifically generated synthetic math data to boost its reasoning abilities.
Got it. So that's pre-training. What about the supervised fine-tuning, the SFT stage?
For SFT, they used a wide range of instruction following and conversational data sets, things like Wild Chat, WizardLM, Evil Instruct, plus synthetic data sets designed to test reasoning and handling complex instructions. They even had a specific chat template they used to structure the conversations during training.
And they made an interesting discovery during SFT, didn't they? About the loss calculation.
They did. They found they achieved better results by summing the loss across all the tokens in a training batch instead of averaging it, which is the more common approach.
Oh, wonder why that helped.
Not entirely clear from the summary, but they also found they needed to use a relatively larger learning rate and train for a longer duration compared to fine-tuning full precision models of a similar size to get the best performance out of this one-bit architecture.
So it behaves a bit differently during fine-tuning too. Makes sense. And the final stage, DPO.
Right, direct preference optimization. This is particularly noteworthy, as you said, because it lets them refine the model based on human feedback, which responses are good, which are bad, without the whole complexity of training a separate reward model.
Yeah, reward modeling can be tricky.
They use preference data from datasets like ultrafeedback and MagPie for this alignment step. They train it for I think just 2 epochs with a specific learning rate and a DPO beta parameter they mentioned.
Okay, relatively quick alignment phase. They also mentioned using optimized kernels from something called the Liker kernel library for this part.
Right, probably for speed and efficiency during that DPO training.
Okay. Now, we touched on post-training quantization earlier, PTQ. How does BitNet stack up directly against models that have been quantized after training? Table 2 in the report looks at this, right?
Exactly. It provides a direct comparison between BitNet b1.58 2B and INT4 quantized versions of Qwen 2.5 1.5b. They used popular quantization techniques like GPTQ and AWQ for the Qwen model.
INT4, so 4 bits per weight. Still low, but not as low as BitNet's 1.58.
Right. And what's really remarkable for you to know is that even though those INT4 methods significantly shrink the memory footprint of the original full precision Qwen model, BitNet b1.58 2B still achieves an even smaller memory requirement.
Smaller than INT4.
Yeah, just 0.4 gigalbit for BitNet compared to 0.7 gigabit for the INT4 quantized Qwen models.
Wow.
But here's the real kicker. Despite using even less memory, BitNet actually maintained stronger overall performance across the evaluated benchmarks compared to those INT4 quantized models.
So it's smaller and better performing than the PTQ versions.
Generally, yes, based on the results. This strongly suggests that training a model natively with these very low precision weights might just be a far more effective way to get efficiency without sacrificing so much performance.
There's a better point on that efficiency performance curve we talked about earlier. It pushes the boundary.
Definitely. Then Table 3 broadens the comparison, looking at other publicly available models that are either natively 1-bit or have been post-training quantized down to around that 1.58-bit level.
So comparing BitNet to its closest peers, essentially.
Right. This includes models like Bonsai 0.5b and Oma BitNet 1b as native examples, and then some larger models that were quantized after training, like Falcon 3 1.58-bit 7b and Llama 38b 1.58.
So smaller native ones and larger quantized ones, how did BitNet do?
The results here are pretty compelling. BitNet b1.58 2B4T consistently demonstrates significantly stronger overall performance than all the other 1-bit models they compared it against in that table.
Really? Across the board?
It achieved the highest scores on the majority of the benchmarks listed there.
That's quite a feat. So it's not just outperforming the smaller native 1-bit models.
No.
It's also doing better than these much larger models, like 7 billion and 8 billion parameters that were compressed down to a similar bit width after being fully trained.
Exactly. Which really highlights the effectiveness of their native 1-bit training strategy. It seems to preserve capability much better than post-training compression, at least in these comparisons.
Okay, so the model architecture and training seem solid. But of course, all this potential for efficiency in the model's design needs to actually translate into the real world when you're running it, right? Inference is key.
Absolutely. So the researchers also dedicated significant effort to optimizing how to run these 1-bit models efficiently.
Which isn't straightforward, I imagine, because standard computer hardware, your average GPU or CPU, and the software libraries like PyTorch or TensorFlow, they aren't really designed or optimized for this, let's face it, pretty unusual combination of 1.58-bit weights and 8-bit activations.
Exactly. There's no built-in instruction for multiplying a 1.58-bit number by an 8-bit one.
Right. So for running BitNet on powerful GPUs, they had to develop a custom CAD kernel.
CADA being NVIDIA's platform for GPU programming.
Yep. And since you can't directly store 1.58 bits efficiently in standard memory types like INT8 or Float16, they came up with this clever workaround. They call it a pack, store, load, unpack, compute approach.
Okay, break that down.
Basically, they group multiple ternary weight values, the made each one of 0 plus 1s together, and pack them into a standard 8-bit integer. This allows for more efficient storage and transfer within the GPU's memory hierarchy.
Ah, clever packing.
Then when it's time for the actual computation, the matrix multiplication, they load these packed 8-bit values into the GPU's really fast on-chip shared memory. Then they quickly unpack them back into their original made each 0 plus 1 form.
Just before they're needed.
Exactly. And then they perform the necessary matrix multiplications with the 8-bit activations. This whole strategy pack, store, load, unpack, compute. It's all about minimizing the amount of data that needs to be moved around the GPU because memory bandwidth is often the biggest bottleneck for these kinds of computations.
Makes sense. Minimize data movement.
They even mentioned using their own framework called Ladder to help with these low-level optimizations. But it's important to remember, as they note, even with this custom kernel, current GPUs aren't inherently designed for optimal 1-bit operations. There's likely still room for improvement with future hardware.
Okay, so that's GPUs. What about running it on CPUs, like in my laptop or phone?
Right. For that, They created BitNet.cpp. This is essentially a C++ library that provides highly optimized computational kernels, specifically designed for standard CPU architectures, but tailored precisely to their 1.58-bit weight and 8-bit activation quantization scheme.
So custom math routines for CPUs.
Pretty much. The goal of BitNet.cpp is to enable fast and, importantly, accurate inference directly on CPUs without needing any specialized hardware. It's designed to be consistent with how the model was trained, ensuring you don't lose accuracy just because you're running it on CPU.
And they've open sourced this code.
Yes, they mentioned the code is publicly available, which is great for developers who want to experiment with running BitNet efficiently on CPUs.
Okay, so let's bring it all together then. What are the big picture implications of this research? Why should you, as someone interested in the cutting edge of AI, really pay attention to BitNet b1.58 2B4T?
Well, I think what's truly fascinating is that this model serves as a really powerful proof of concept. It strongly suggests, maybe even challenges the assumption, that achieving high levels of performance in large language models necessarily requires the full precision we've traditionally relied on, at least maybe not for models of this 2 billion parameter scale.
And that has the potential to really change who can access and utilize powerful AI, doesn't it?
Absolutely. If these models can run efficiently on less demanding hardware, it just blows open the possibilities for deploying them in resource-constrained environments, maybe directly on edge devices like your phone or sensors.
Yeah, offline AI assistant.
Exactly. And in real-time applications where the massive computational requirements and latency of current huge LLMs simply aren't feasible. Imagine having sophisticated AI assistants running directly on your devices without needing that constant power-hungry connection to the cloud.
That would be a game changer.
This research also clearly points the way to a number of really compelling future research directions. The researchers themselves mention the exciting prospect of scaling these 1-bit models up maybe to 7 billion, 10 billion, 70 billion parameters and training them on even more vast data sets.
Seeing if this efficiency holds at larger scales.
Right. And there's also the potential for hardware co-design. Imagine creating new generations of computer chips, CPUs, or specialized accelerators that are specifically optimized for these low-bit operations. That could unlock even greater efficiency gains down the line.
They're also looking into other areas, right? Like context length.
Yeah, extending the length of text these models can process effectively. That's crucial for understanding longer conversations, documents, you name it. Also, investigating multilingual capabilities, getting them to understand and generate text well in multiple languages, not just English.
And multimodal.
And integrating them with multimodal AI models that can understand not just text, but also images, audio, maybe other data types. Plus, just delving deeper into the fundamental theory, why does 1-bit training at this scale work so well? Understanding that could lead to even better techniques.
So lots of avenues to explore.
Definitely. All of this indicates that BitNet b1.58 2B4T isn't just some interesting academic exercise. It really could represent a significant step towards a fundamentally more efficient, more accessible future for large language models. And that could impact how you interact with AI in the years to come.
So the key takeaway for you, the listener, is this. BitNet b1.58 2B4T provides pretty compelling evidence that high-performing LLMs might be achievable with significantly less computational cost, less memory, less energy, maybe faster speeds than we previously thought.
Yeah, that's the core message.
And this could really revolutionize how and where we can deploy advanced AI.
Remember that initial challenge we talked about, needing supercomputers for advanced AI? BitNet offers a promising pathway towards more efficient models that could potentially run much more easily on more readily available hardware. It could bring that advanced intelligence to a much wider range of applications and users. Democratization, like you said.
So if you're interested in exploring this further, digging in yourself, you can find the BitNet b1.58 2B4T model release on Hugging Face.
Pretty easy to find.
And you can even check out their open source inference code, that bitnet.cpp library, and the CUDA stuff. They give a link, https://aka.ms/bitnet.
Right.
And of course, for those of you who are really technically inclined, the full technical report itself is the ultimate deep dive into all the details.
So maybe this leaves you with a fascinating question to consider. Could this type of research, this focus on extreme efficiency, be a pivotal moment, a turning point where truly powerful AI becomes genuinely accessible to a much broader audience, maybe everywhere?
Yeah, and following on from that, what novel applications and innovations might we see emerge if LLMs like this could operate efficiently right there on our everyday devices? What becomes possible then?
Things we haven't even thought of yet, perhaps.
Some truly thought-provoking questions to consider. Thanks for joining us for this deep dive.